Hello guys. So this is the video for the lecture for the first Friday that you guys are going to watch online. This is for Friday, May 13, 2022. Okay, so last time on Wednesday in class, we talked about the notion of limit. And the way we approached this was using an intuitive approach. Okay, so let me remind you a little bit what we discussed last time. Basically, the main idea is that anytime that you have something like this, okay, there is essentially, a statement, a sentence that we're saying whenever we write this. So when you write the limit as x approaches a of a function f equals a number L, what we are really saying is that the values of the function get very, very close to L whenever x is very close to a from either side. Okay. So of course, if you are given, for example, this problem, or let's say this one over here, because we already have the formula, without the answer on the right, of course, the question that you need to answer is the function x squared minus 9 over x minus 3 getting close to some specific number whenever x is close to 3? Okay, that's what it means to compute the limit. And what we discussed last time is that to answer such a question, there are different techniques, and the ones that we talked about, we mainly talked about two ideas. First, numerically, in other words, just start plugging in points, numbers that are very close to the value that you want to approach with x. In this case, it was 3, from either side, from the left and from the right, and then we observe the behavior of the function, the outputs. And if we see that all the numbers, the outputs of the function, are getting closer and closer to some specific values, we can estimate what the answer should be. The thing about this is that we are not sure, right? Here we're just doing an educated guess that, for example, in this case, it appears that the answer will be 6. To overcome this difficulty that we don't want to be guessing, then we talked about another idea, which is graphically, right? So if you can graph the function, you basically can answer almost any question that is thrown at you about this function. So we can use it to compute limits. We want to know what happens to the function when x is close to 3. Okay, we sketch the graph of the function. In this case, this was something that we could do pretty easily. It's a line with a hole, right? And then we can see by looking at the picture that when you are close to 3 from either side, the values of the function approach 6. So now we're sure that the answer is 6. But as you understand, this is not a viable method in general, just because usually we don't have the graph of the function. And to produce a graph is actually a hard job in general. When the function is easy like this one, it's okay. But if we have something more complicated, then we cannot rely on this method. So today what I want to do is let's talk about a third method, which is actually the preferred one, which is algebraically. So let's learn how to compute limits algebraically without having to rely on a table of values and without relying on a graph so much. Okay, so that is the idea for today. Okay, so to begin, I'm just gonna write down some basic properties, and the reason why these properties are true should be pretty obvious once I write them. Okay, so let me begin by writing here basic properties. So again, these are very basic and should have no problem understanding why these statements are true. So let A and B be real numbers and N a positive integer. Okay, then we have the following. So number one, the limit as x approaches a of b. Let's start to figure out what that is. Then number two, the limit as x approaches c of x, say a, equals, and then number three, the limit as x approaches a of x to the n equals. Okay, so let's try to answer this question. And by the way, what I'm about to write now here is the proof of each of the statements that we are going to complete right now. Okay, so for the first one, what is it that we're analyzing? So in this case, the number b is taking the role of a function, right? It's actually the constant function. So let's think about the graph of it for a second. How does the function y equals b looks like? Well, that's just a horizontal line. Let's say that we have b over here. It doesn't matter if it's positive or negative. This is just an example. This is how it will look, okay? And let's say that a is somewhere in here, then it should be clear that, when you get close to a from either side, of course, the values of the function are getting close to this number, the y value of this point, which is just b. And this happens at any point, no matter what a is, this will always be the case because this is a constant function. So, moral of the story, the limit as x approaches a of a constant is just the constant, right? So it's equal to b regardless. So as the first basic property, the second basic property is what we do when we compute the limit of the line y equal x, right? That's the function in question, y equal x. Well, once again, we can answer this question by relying on the graph really quick. The point is that we only do this once with the graph, then we don't have to do it anymore. Then we can just use the property. So y equal x, this is a line passing through the origin, right? With the slope equals 1. So that's y equal x. And then let's say that we have a over here. And then the point corresponding to a is also a, right? Because y is equal to x. And therefore, when we get close to a from either side, as you can see, the values of the function get close to a as well. In other words, the limit as x approaches a of x is just a. And hopefully this makes sense to you. And then finally, for the last one, for number 3, notice that here the function in question is a power function, x to the n. And here, because n here is a positive integer, so we have that here, n is a positive integer. So once again, I'm going to rely on the graph to justify what the answer would be. There are two cases that we need to analyze. First of all, when n is equal to 0, then x to the 0 is just 1. So we are in the constant case. That's property number 1. When n is equal to 1, then x to the n is just x. So we are in property number 2. So what's interesting here is to see what happens when n is 2 or larger. And we're going to divide this in two cases. If n is even and when n is odd. Okay? Like for example, if you want to have something in mind, think about x squared for a second. And here, think about x cubed for a second. As you know from pre-calculus, when n is even, then the power function x to the n, looks just like the x squared function. It's just that the bigger n is, the faster it's gonna grow. So it's gonna be closer to the y-axis. But when you look at it from far away, the shape is this, right? In particular, it's a nice little function. It has no holes, no gap, nothing weird going on. Okay. And then when n is odd, then the function is gonna look like the cubic function. So x to a 3, x to a 5, x to a 7, etc. They all look similarly. When you look at them from far away, they are gonna have the same sort of shape. It's just that the higher the power, the faster they grow, and then between 0 and 1, between -1 and 1, the graph is gonna be closer to the x-axis and so on. But the general shape is the same. And once again, no hole, no gaps, nothing weird. In both of these cases, let's say we have a over here, a over here, then you can clearly see that because there is nothing strange happening with the function, when you approach a from either side, then we get close to the value of the function, which in this case, for example, if this was, this would be a to the n. In the case of n equals 2, then it would be a squared, okay? And this one here would be Once again, a to the n. If it's n equals 3, then it will be a cubed, etc. So the point is that all we have to do to find the limit is evaluate the function at that point. So once again, the answer here is a to the n. Okay, so these are our basic properties. The limit of a constant is just a constant. The limit of the function y equal x as x approaches a is just a. And the limit of the power function x to the n as x approaches a, you just evaluate and you get a to the n. So let's see, let's look at some quick examples for this. Let's see, find the limit. And let's see, limit as x approaches to 3. And let's do limit as x approaches -4 of x. And then let's do the limit as x approaches 2 of x squared. So the first one, this is actually our basic property number 1, right? So we are dealing here with the constant function y equals 3. And as you know, this limit is just 3. So when x approaches 2, the y approaches 3. I mean, our y is always 3 anyways. So this limit is equal to 3. Part B, this is actually, property number 2. We can use property number 2 for that one. This is just -4. Evaluate, we get -4. And then part C, that's property number 3. And this would just be 2 squared, which is 4. Okay? So it should be pretty straightforward to use these basic properties. Okay, so those are the basic properties. Now let's see how we use those basic properties to our advantage. And to be able to do that, I need to give you some more properties that are a little bit more interesting. These are the algebraic properties of limits. Okay, and if you have questions about why some of these properties are true, then you're welcome to ask me in class when we meet next time or during office hours. But it should be somewhat intuitive why what I'm about to write is true. Okay. Okay. So algebraic properties. And what I mean here is how do limits behave with respect to the algebraic operations, right? So for example, how do limits behave when we do addition of two functions, when we subtract two functions, when we divide, when we multiply? That's what these properties are about. And the answers is what you will expect. The limit of the sum of two functions is going to be equal to the sum of the two limits if they both exist. And same thing for the difference, the product, and the division. Okay? All right. So let A and B be real numbers. So real numbers and a positive integer. Okay. Also, suppose that we have two functions. So let f and g be two functions with the following condition. So such that, let's say that we know their limits, okay? Such that the limit as x approaches a of f, let's say this limit equals L, and let's say that the limit as x approaches a is important. Notice that it's the same point, okay, of the function g. Let's say that this limit is k. Again, I stress the fact that the limits, they are both approaching the same point, okay? So if this happens, and here L doesn't have to be the same thing as K. They could be equal, but they don't have to, okay? So under these conditions, then we have the following. So then, number 1, the limit as x approaches a of the sum of the two functions. Well, actually, before I talk about the sum, let me talk about this one, of b times f. So, you have the function f. Remember that b is a constant, it's just a real number. Then you can always make a new function by multiplying our function f by a constant. So this is basically a stretch, right? Either a stretch or a compression of the graph. There could be some flipping if b happens to be negative. The point is that if you take the limit of b times the function, we can actually take the constant out of the limit. So this is going to be the same as b times the limit as x approaches a of f of x, and therefore the answer will just be b times L. And this makes sense. Remember, the limit of f is equal to L. So we are saying that the values of f are close to L whenever x is close to a. So if you multiply the function by b, then the new function that you obtain, the values are going to get close to b times L. So hopefully that's very intuitive to see. Okay, so that's the first one. The fact that we can take constants out of a limit. Okay, we can factor out a constant out of a limit. Okay, so second property number 2, is the fact that if you take the limit of the sum of two functions or the difference, I'm going to put two properties in one. Okay, this means sum or difference of two functions. This is going to be the sum or the difference of the limits, depending what you're doing. All right, in other words, this is going to be L plus or minus K. Again, the plus is if you're adding, the minus is if you're subtracting. Okay, and remember, you can do this because we already know that the individual limit exists. Okay, so if one of the functions, the limit does not exist, you cannot play this game. You cannot separate the two limits. We can do that just because we know that the limit of f exists is equal to L and the limit of g exists is equal to K. If one of them does not exist, you cannot use this property. Okay, so number 3, similarly for the product. So all of this is provided that both limits exist. So the limit of the product of two functions equals the product of the limits. Limit as x approaches a f of x times limit as x approaches a of g of x. So this is L times K. Okay, so we have those two properties. Let me actually keep this in black. Okay, so we have these properties. Now there is another one, the one for division. And again, just like for multiplication, addition, subtraction, the limit of the quotient is the quotient of the limits. There is just a small note that we need to make, which is this is provided that the limit of the denominator is not 0. Because as you know, division by 0 is not defined. Okay. So limit as x approaches a of f over g. So this is going to be equal to the limit of x approaches a of f divided by the limit as x approaches a of g. So that's equal to L over K, and this is provided. So this happens if K is different than 0, of course. Okay, if K is equal to 0, and you cannot do this, we see what we do. Okay, so in the next section, we're going to address that question. There will be two main cases. It depends on the top. If the top is also 0, so if L is 0, you will have 0 over 0. Then we get what we call an indefinite form, an indeterminate form. Okay, and then we're gonna discuss some techniques to deal with this, and then later in the course we're gonna learn how to deal with 0 over 0 in general. And then the other situation would be if L is not equal to 0. If L is a number different than 0, and then K is 0, when you divide a number, when we say that K is 0, what we're really saying is that, K, the limit of G is 0. In other words, the values of G are getting smaller and smaller every single time when you approach A. So you're not really dividing by 0. It's just that you're dividing by values that are very, very, very small. So When the top is a fixed number, approaches a fixed number, and the bottom is getting smaller and smaller all the time, what happens to your fraction is it's going to get bigger and bigger and bigger, either in the positive or negative direction. It depends, whether we are getting positive or negative numbers. So this is going to give us something like positive or negative infinity. And we kind of saw this last time when we saw the function 1 over x, right? This is a situation in which the top is a 1 and the bottom, if you approach 0 from the right, what happens? It shoots up to positive infinity. So that limit does not exist, but we're going to say in the next section that we're going to say in that case that the limit will be positive infinity. If you do it from the left, then the values of the function goes down to negative infinity. So we will say the limit is negative infinity. We're going to we're going to discuss this in the next lecture, okay? But for now, let's just use this property for the quotient provided that the denominator is different than 0. Because when it's equal to 0, there is some analysis to be done, okay? Okay, so that's number 4. And then for number 5, we have the limit as x approaches a of f of x, and then let's raise this function to the n power. And if this happens, this is basically the limit. So we just take the limit of the function, and then we can raise it to the n power, the result. In other words, this is L to the n. Similarly with roots. So if you have the limit as x approaches a of the n root of x, this would just be the n root of a. Okay, and I should probably, okay, let's just keep it like that, and then when we talk about continuity, and you will see that this actually can be extended to not just x, but I could put just a function here. And then if you put f inside that radical, then the statement would read the n root of L, where L is the limit of the function. Okay? But let's keep that after we do continuity. Okay, so these are our algebraic properties for limits. So remember, the basic ones are the limit of a constant is just a constant, the limit of the function x is just the value that you're approaching to, and the limit of x to the n, you just evaluate it, a to the n. Okay? Then for the algebraic properties is the fact that we can factor constants out of a limit, and the limit of a sum or difference is the sum or difference of the limits, provided that both exist. Limit of the product is the product of the limits, as long as both exist. Same thing for the quotient. We need to make sure that the bottom is not equal to 0. And then we can say that the limit of a function raised to a power is going to be equal to the limit of that function, which is just L, for example, raised to the power. Okay? And same thing with the radical. If you have a radical, then you just evaluate the radical. A little note that I'd like to make here is this is, so if n is even, then we need to have a greater than 0, right? And if a is equal to 0, then our limit, and if a is equal to 0, then the limit should be as x approaches 0 from the right. And this is just because of the domain of the function, because when the index is even, like square root or the fourth root, that function is not defined for negative values. So it doesn't make sense to compute limit as x approaches -3, for example. Okay? And if you want to approach 0, you can only do it from the right, because there is nothing to the left of 0 that's in the domain of that function. So that's just a little remark here. Technicality for problem number 6. Okay, so I'm gonna show you a couple of examples, and then we're gonna see, I mean, if you want to really use this property, the problem will be a little bit long and tedious, but the point is that these properties will allow us now to easily compute a bunch of limits. For example, we'll be able to easily evaluate limits of any polynomial function, any rational function, and so on. So I'm going to go ahead and do 2 examples in which I'm going to use the properties one step at a time, but we typically don't write every single step. We just do everything at once, okay? You will see what I mean in a second. Okay, so examples. And make sure that I'm still there. Yes. Okay, so as an example, let's find the limit. So find the limit, and let's do limit as x approaches 2 of the function 4x squared plus 3. So again, here we don't want to rely on any graph and we don't want to rely on any table. We just want to compute this limit. Now we can use the properties. So notice that if we look at each of these, there are two functions here. We have this one, we have this one, right? And both of those functions, we can find the limits. The second function is a constant, so we know what the limit is. And the first function is a constant times x squared. We know how to deal with those limits by using the properties, okay? So we can say that we can use the property that says that the limit of the sum is the sum of the limits, okay, plus the limit as x approaches 2 of 3. Now we can immediately evaluate this second limit over here by using one of the basic properties. To evaluate the first one, we need to use another algebraic property that says that we can take constants out of a limit, right? So that 4, this 4 over here, we can take it out. So we can write as 4 times limit as x approaches 2 of x squared. And I'm going to evaluate the second limit. Because 3 is a constant, then this limit is just 3, right? Be careful, don't get confused, and don't write that the limit is 2. The limit is 3 because we have the constant function 3. And now we can evaluate this other limit over here because this is the x squared function, and as you know, this we just evaluate, so that's 2 squared. So this becomes 4 times 2 squared plus 3, or 4 times 4, that's 16, plus 3, which is 19. Okay? All right. So again, here we use several of the properties listed above. As another example, let me do the limit as x approaches 1 of x squared plus x plus 2 divided by x plus 1. Okay, so here this is a quotient of two functions, so I would like to use the property that the limit of the quotient is the quotient of the limits. We just need to make sure that the limit of the bottom is not equal to 0 to use that property. In this case, we see at the bottom the limit is 2, right? When x approaches 1, x plus 1 is going to approach 2. So we are good to go. So we can split this. As I said, in these two examples, this is the only time that I'm going to be doing this one step at a time. Because typically we just skip all of these steps and move straight to the answer. Okay, so as one of the properties, then we can use the other property on top to say that the limit of the sum is the sum of the limits. We wrote the property with two functions, but this can extend to as many functions as you want, okay? So if we're adding 3 functions, then that means that there are 3 limits here. Limit as x approaches 1 of x squared, plus the limit as x approaches 1 of x, plus the limit as x approaches 1 of 2, over, same thing in the bottom, limit as x approaches 1 of x, plus limit as x approaches 1 of 1. And now it's time to evaluate because all of these are simple limits. So the limit of x squared, so that's just 1 squared plus 1, and then the last one is plus 2 because that's a constant, and then here we have 1 plus 1. So at the end, what do we have? 1 plus 1, 2 plus 2, 4. So that's 4 on top, 2 in the bottom. That's equal to 2. Okay? All right, so let's reflect on this for a second. Notice that for the first limit, at the end of the day, if we look at this expression right here, all we are doing really is just evaluating the function at 2, right? So we have a polynomial function, 4x squared plus 3. And after using the properties, it turned out that actually all we have to do is plug in x equal 2, and then we get the answer to the limit. And this is true in general for any polynomial functions. The point is that polynomials are nice functions. They don't have any hole, no gaps, nothing weird. If you remember from pre-cal, The graph of a polynomial function is what we call continuous. We're going to make this precise later, but the formal idea is that you can draw the graph with lifting your pencil. So that means that if you get, when x is getting close to a certain point, the y values are going to get close to whatever the value of the function is at that point. Okay, so, and also you can think of it as by using the properties. A polynomial is just a sum of monomials, terms like 4x squared, 3x to the 7, stuff like that. So all you have to do is split. When you find the limit, you just write as a sum of a bunch of limits, sum or difference, and then evaluate each of those, and then you add or subtract. So you're just evaluating the function. Similarly with this rational function, okay? Notice that in this case, the bottom is different than 0 at 1. So 1 is part of the domain of the function. And it turned out that at the end of the day, if we look at this last part here, all we did was plugging 1 into the function, and that gave us the answer. So that's true in general as well. So to find the limit of a polynomial function, just plug in. To find the limit of a rational function, just plug in, as long as the denominator is not equal to 0. Okay, if you get 0 in the denominator for rational functions, then we have to talk about that. So in other words, from now on, if you see this limit as x approaches 2 or 4x squared plus 3, we will not be writing all of those steps anymore. We will just say, okay, that's just equal to this. So you immediately go ahead and evaluate. Oops, 19. Okay, and similarly for the other one, if you see limit as x approaches 1 of x squared plus x plus 2, something like this, then we just quickly check. We see that this bottom, when you plug in, you don't get 0. So you immediately say, okay, this is just equal to this, which is, evaluating. So the limit of the top is 4, the limit of the bottom is 2. So that's 2, that's equal to 2. So as simple as that. Just evaluate the function at the point, in the case of polynomials and rational functions. So let me write that down. And it will turn out that actually most of the functions that you know, this is what you do. You just evaluate when you compute the limit, okay? We just need to deal with cases that will give us something special like 0 over 0 and stuff like that. And we're going to pay our attention on that later. Okay, so let's summarize what I just mentioned. Limits of polynomial, rational, and transcendental functions. Transcendental functions are the order trigonometric functions, sine, cosine, tangent, secant, cosecant, cotangent, and also exponentials and logarithmic functions. Okay. All right. So as a direct consequence of the properties above, I'm gonna call corollary. That means direct consequence of what we have discussed. We have the following. So let a be a real number. Then we have the following. So number one, if p of x is a polynomial function, then when you find the limit, all you have to do is plug in. Then limit of x approaches a, p of x is just the value of the function at a. It's p of a. Oh, by the way, let me make a remark here. All of these properties that I said about limits, they of course also apply to psi limits. Okay, so these basic properties, if we are taking psi limits, like limits from the right or limits from the left, they also apply identically. And similarly for the algebraic properties, they all work for psi limits as well. So let me maybe make a remark here. So remark, all of the above properties are also valid for psi limits, okay, either from the right or from the left. The limit of the sum is the sum of the limits, and so on. You just need to be consistent. If you're doing it from the right, it has to be both limits have to be from the right, or both from the left. Okay, you cannot do a mixture of those. But all of those properties apply. Okay, so the limit of a polynomial function is just just evaluate, and once again, same thing for side limits. And number two, if you have a rational function, so if r of x, so rational function means that it's a quotient of polynomials. Okay, it's p over q. It's a rational function. It's a rational function with, and let's say that the denominator q is not equal to 0 at a. Okay, in other words, what I'm saying here is that a is part of the domain of the function, of this rational function. So if this happens, then if you want to know the limit, is just evaluate. Then the limit as x approaches a of r of x is just the value of the rational function at a. So for polynomial functions, rational functions, you just plug in when you take the limit, as long as the value that you're getting close to with x is part of the domain of the function. Polynomials domain is all real numbers, so you don't have to worry. You just plug in. Rational functions, the domain is not necessarily real numbers. You always have to make sure that the bottom is not equal to 0. So just be careful if you're taking a limit when the denominator at a value that makes the bottom equal to 0. In those cases, then you need to do something else that we will discuss soon. Okay, so we have this for polynomial functions, for rational functions, and the same idea holds for all the transcendental functions. And to justify those, just think about the graph of sine, cosine, right? Those are nice graph, no gaps, no holes. So you can uh, just plug in the value when you take the limit, okay, as x approaches a certain point. For tangent, then you have to be careful. Remember the tangent has a bunch of vertical asymptotes because it's not defined whenever cosine is 0. And cosine is equal to 0 at odd multiples of pi over 2, right? So cosine is 0 whenever you have an odd multiple of pi over 2, like pi over 2, 3 pi over 2, 5 pi over 2, etc. And therefore, the tangent is not defined there. But other than that, you just, when you take the limit, you just plug in. And same thing for the others. Okay? So limits of transcendental functions. So transcendental functions. So for sine and cosine, there's nothing to worry because the domain is all real numbers. So the limit as x approaches a of sine of x, this is just sine of a. Okay, there's nothing to worry about there. Similarly for cosine, limit as x approaches a for cosine of x is cosine of a. But now for the others, you have to make sure that a is in the domain. So number 3, the limit as x approaches a of tangent is equal to tangent of a if a is in the domain of tangent. Which I remind you what this means. So remember that tangent of x is sine over cosine. So essentially, what I'm saying here is that you can just evaluate provided that when you do cosine of a, this is different than 0, right? Because the domain of the tangent function is all those values of x for which, as long for which cosine is different than 0, okay? Okay, so you just plug in as long as the point that you're approaching to is part of the domain of the function. And then similarly for secant, cosecant, cotangent. So all the functions that are defined like a fraction, you always have to be careful with this. So similarly for the functions y equals secant, y equals cosecant, and y equals cotangent. Okay, same idea. You just plug in as long as the value is in the domain of those functions. Okay, so then let's talk about the logarithm and exponentials. So the limit as x approaches a of b to the x, this is going to be equal to b to the a, and this is provided. So remember that when we have the exponential function, let me just so recall the exponential function. This is the function y equals b to the x. And whenever we talk about exponentials, there are some restrictions that we have. The first one is that the base has to be positive and different than 1. Okay? And then in this case, let me remind you of the graph because it's going to be helpful for us later on. Okay? So the graph, there are two versions of the graph. It depends on the base, whether it is bigger than 1 or less than 1. So if b is bigger than 1, then the way the exponential function looks like is an increasing function. So it has this shape, and it always, when you plug in 0, you get 1. And then when b is between 0 and 1, if the base is between 0 and 1, then it's a decreasing function. So it's the graph that we have here in red, but reflected about the y-axis. In other words, we have this behavior. Okay, something like that. Wait, it doesn't touch the x-axis. Oh, there we go. And once again, it goes through 1. Okay, so this is how the exponential function looks like, depending on whether the base is bigger than 1 or not. For example, the function e to the x looks like the red graph because the base will be e, and e is 2 point something, right? So it has base bigger than 1. Anyways, the point is that regardless of which one of the two cases we are, notice that in this case, when you look at the graph, there is nothing strange. There is no hole, no gaps, nothing. So if you want to take the limit, at any point, you just evaluate the function at that point because domain is all real numbers and there is nothing strange with the graph. So the limit as x approaches a of b to the x is just b to the a. So just evaluate. Okay. All right. So that's for number 4. Okay, we're gonna do examples now in a second. Let me just put logarithmic function. So logarithmic functions. Now, in the case of logarithms, okay, uh, of course we can write this. I can, okay, I'm gonna write the property for a general logarithm, but I want you to understand that everything is enough to just study ln. Okay, we can write everything in terms of ln, and this is because of the change of basis property. So let me actually get that out of the way. So let's see. So remember that when we define y, when we have y equals log base b of x, right? So once again, the logarithm is defined as the inverse of the exponential function. So the base is b, so again, it comes with the same restrictions. It cannot be, so it has to be positive and different than 1 base. Okay. Now, remember the domain is x greater than 0. In other words, the domain is from 0 to infinity. You cannot do the logarithm of a negative number. And if you don't remember the definition well, remember that this means that if you do b to the y, then we get x. In other words, log base 2 of 8, this is equal to 3, since 2 to the 3 is equal to 8. In other words, a logarithm is just an exponent. What exponent? The exponent for which you need to raise the given base to get the given number. So if you do log base 2 of 8, what you're asking is, to what power can I raise 2? 2 to what power equals 8? Okay, and the answer is 3, which is what we get here. Right, so that's our logarithmic function. And if, as you know, the graph of the logarithm, just like for exponentials, it depends on the base. If the base is bigger than 1, it has a certain shape. If the base is between 0 and 1, then it has another shape. So let me put that here. So if the base is bigger than 1, the logarithmic function looks as follows. So again, the domain is from 0 to infinity. So it's only on the positive part of the x-axis, and this is how it looks. Okay, it goes through 1, and it has this shape. And notice that when we get close to 0 from the right, the function goes down to negative infinity. Okay, and then if the base is between 0 and 1, then the function looks like this. It's reflected about the x-axis, so it's going to have this shape. In this case, when we get close to 0 from the right, then the function approaches positive infinity. Okay, so that's how the logarithmic function looks. Once again, as long as you approach a number that's in the domain of the log, then all you have to do is evaluate the function in the log, because there is nothing strange happening. Okay, so let me write the general property. So limit as x approaches a of log base b of x. This is just log base b of a if a is in the domain. In other words, if a is bigger than 0. Of course, if a is not is less than 0, then it does not even exist, because there is no function to look at. It's not part of the domain. All right. So what I was saying is, for example, the function, the natural log function, which is the one that you're going to be seeing a lot, ln of x, actually is a case like the red graph here, because the base, so remember, so recall that the function y equals ln of x, this is just a logarithm with base e. Okay, it's just a logarithmic function with base e, but e is bigger than 1, so that means the natural log function looks like the red picture. So this is the graph. This is how it looks like. And when you plug in e, that's when you get 1, right? So if you plug in e, then you get 1, because ln of e is equal to 1. So that's the graph of ln of x. And therefore, if you find the limit of a natural log function, all you have to do is evaluate the function, okay, at the value you're approaching to, as long as it's part of the domain. But in general, any other logarithm can always be written in terms of ln. So from now on, whenever we want to study logarithmic functions, we will just talk about ln, okay? I'm not going to talk about the general log, because of the following. So we have the change of basis property. So this is number 1. And also number 2, remember that if you have any log, let's say base b of x, you can write this as ln of x over ln of b. This follows from the change of basis property. And now ln of b, this is just a constant. So I can write this as 1 over ln of b times the function ln of x. So the thing is that this now is a constant. This is a constant. So if you understand the natural log function, then if you want to analyze any other logarithmic function, that's just understanding the natural log times a constant. What constant? 1 over ln of whatever the base is. Okay? So in particular, if we're computing limits, as long as you know how to take the limit of an ln function, then you immediately can take the limit of any other logarithmic function by using this equality that we have here. Okay, so just keep that in mind that from now on I will just be focusing on the natural log function because any other logarithm can be written in terms of ln in this way. Okay, all right, so this was a small refresher of some stuff that you know from pre-calculus. So let's go ahead and let's do some examples now. So examples. So let's find the following limits. So find the limits. And let's see, number one, limit as x approaches 0 of tangent function. Number two, the limit as x approaches 7 pi over 6 of sine cube. 3, limit as x approaches -1 of x times e to the x. And then let's do limit as x approaches e of ln of x cubed, like this. Okay, so for the first one, the question is 0 part of the domain of the tangent function? And the answer is yes, because tangent of 0 is equal to 0. Remember, tangent is sine over cosine, and sine of 0 is 0, cosine of 0 is 1. Okay, so this would just be tangent of 0, which is equal to 0. So no problems here. For this one, notice that here we're calculating the limit as x approaches 7 pi over 6 of the sine cube of x. So in this case, this right here, we need to use one of the properties. Remember that says that when you have a function raised to a power, then the limit will just be whatever the limit of the function is raised to the power. So this is the limit of the sine function as x approaches 7 pi over 6, and then we raise that to the third power, and the limit of the sine function we just evaluate the sine of 7 pi over 6, and then we cube it. Now what's the sine of 7 pi over 6? So remember that this is, you need to use one of the special angles here. So again, a small refresher. So remember there are some angles that you need to know, and those are 30 degrees, 45 degrees, and 60 degrees in quadrant 1, that you need to know the sine, the cosine, tangent, etc. Once you know those sine and cosine, then you know everybody else because of the quotient identities. So in radians, 30 degrees is pi over 6, 45 degrees is pi over 4, and 60 degrees is pi over 3. Okay? So you need to know pi over 6, the sine of pi over 6. And why am I mentioning pi over 6? Well, because 7 pi over 6 is actually over here, right? It's in quadrant 3. How do we know that? Because 7 pi over 6, we can write it as pi plus pi over 6. In other words, you do 180 degrees, so you do pi, and then you do an extra pi over 6. So this right here is 7 pi over 6. Okay, so it's in quadrant 3. And the important thing in doing this splitting is that it's pi plus pi over 6. So that tells me that this little angle here measures pi over 6. Okay, that little angle over there is pi over 6. And that angle is special. It has a name. This is called the reference angle of our angle 7 pi over 6. So remember, the reference angle is the acute angle made between the terminal side and the x-axis. So when you have an angle that's not in quadrant 1, in either in quadrant 2, 3, or 4, we can always compare that with an angle in quadrant 1. That one will be your reference angle. And the way you find it is by looking at the acute angle between the terminal side and the x-axis. For example, in quadrant 2, if this is your theta, the reference angle is this guy over here, alpha. That's the reference angle. So let's say alpha reference angle. At the quadrant 2 case, the quadrant 2 picture, the quadrant 3 picture, which is the situation that we have here. We have an angle here in quadrant 3. This is our theta. Then alpha is this one. Be careful, don't say it's this one. Okay, it's not with the y, it's with the x. And then the quadrant 4 situation, we have our angle here. This is our theta. Then alpha is this one over here. Okay, so we can always find if you have an angle that's not in quadrant 1, because in quadrant 1 is equal to its own reference angle. But if it's in quadrant 2, 3, or 4, we can easily find the reference angle by looking at this picture, and therefore there are some formulas that you can that we have, right? Those are called the reduction formulas. For example, in the quadrant 2 case, what's the relationship between alpha and theta? So this is quadrant 2, this is quadrant 3, and this is quadrant 4. So in quadrant 2, the relation is that alpha plus theta equals pi. So if you want to get the reference angle, you just do pi minus theta. Okay? In quadrant 3, which is our example, 7 pi over 6, the relationship is that if you do pi plus alpha, you get theta. So if you want to find the reference angle, just do theta minus pi. So if we take 7 pi over 6 and subtract pi, we're going to get our pi over 6, which is the reference angle. And in quadrant 4, the relation is that if you do theta plus alpha, we get the full revolution, which is 2 pi. So to find alpha, just do 2 pi minus theta. Okay? All right. Now, why am I talking about reference angle? Well, because remember, if you know what happens in quadrant 1, then you can transmit that information to the other quadrants, because something that you learned in trigonometry was that the sine of an angle is always in absolute value the same as the sine of its reference angle. The same thing for cosine, tangent, and the other functions. Okay? So I said in absolute value because, as you know, depending on the quadrant, the sine could be positive or negative. And same thing for the cosine, etc. But if you ignore the plus or minus symbol, if you ignore that for a second, in absolute value, the number that you get is the same as the corresponding reference angle. So to find sine of 7 pi over 6, that would be the same thing as figuring out the sine of pi over 6 itself, but we need to remember, is it positive or negative for 7 pi over 6? 7 pi over 6 is in quadrant 3, and remember sine is given by the y value on the unit circle, of a point on the unit circle, and we are in the place in which y is negative in quadrant 3, right? Down here. Here y is negative. Remember, sine is positive in quadrant 1 and quadrant 2, and then it's negative in quadrant 3 and 4 because that's where y is negative. So this is going to be equal to minus the sine of pi over 6. So I just replace this by the reference angle, 7 pi over 6 by pi over 6, but then we need to decide, do we keep it positive or negative? In this case, it's negative because 7 pi over 6 is in quadrant 3, and we are computing sine, which is negative there. Okay? All right. And now sine of pi over 6, that's 30 degrees. And as you know, sine of pi over 6 is 1/2. So this is going to be negative 1/2 cubed. So we get negative 1/8 as our answer. Okay. All right. So I was a little refresher on some trigonometry as well in this example. Let's continue with number 3. So here we're going to use the property. Here we have a product of two functions, right? The limit of the product is the product of the limits. And in this case, the first function is -1, the limit, and the second function, the limit is e to a -1. So this is -1/e, or -e to a -1. But as you know, we typically don't want to have negative exponents. So when we do, we write it, we bring it to the bottom with a positive exponent. And for number 4, for example, we can do the following. We can see, you could just plug in directly if you like, but again, once we talk about continuity, you will see, because this is a composition, and you will see that here to find the limit, you just plug in as well. But we can use a little property now, and this way I remind you of the property. Remember that ln has the property that when you do ln of some power, it brings the exponents down. So that's the same thing as 3 times ln of x. And now we can use the property of limits, that we can take constants out. So we can take the 3 out, and then times the limit of ln as x approaches e, that's just ln of e. But ln of e is equal to 1, so that's 3 times 1, which is 3. Okay? All right. So in this example, we have, with these 4 examples, you see how we have used in some of these the algebraic properties, and also how to compute with the transcendental functions. Okay. Again, for polynomial rational functions, as mentioned above, we just plug in. Okay. All right. So this is fine, and as long as we can just plug in into the function, we're basically good to go to find the limit. But what if we get in trouble when we plug in? In other words, what if we were to plug in a value and we actually get something that we cannot compute, like something divided by 0 or 0 divided by 0? Okay, what do we do in situations like those, in which just evaluating is not enough? So note, how about, just remember this, the very first one that we did, x squared minus 9 over x minus 3. How about this one? Because this is a rational function. If you try to evaluate, then what's going to happen is that we're going to get 0 in the top and 0 in the bottom. So we cannot use the properties that we have discussed above. How do we answer this question? Okay, so let's talk about this. Again, we know the answer to this one in particular, but this is just a class of problems that we need to discuss. So let's talk about uh, more techniques to compute limits. And now here we're going to introduce the idea that one of your classmates pointed out last time, that we basically can do algebra. Like, hey, why don't you just factor and simplify, and then we get the answer. So let me revisit what we did last time on that. So recall, if we wanted to compute the limit as x approaches 3, x squared minus 9 over x minus 3, one of the approaches was, the one that we were able to obtain the answer for sure, was doing a graphical approach, right? So remember that our observation was that this function, x squared minus 9 over x minus 3, actually is a piecewise function, right? So we saw that this is actually equal to the function x plus 3 as long as the function is different than 3. And that happens by just factoring and simplifying, right? And then it did not exist, this does not exist when x is 3, which means that what I want you to pay attention is when I want to compare this function versus this function. Okay, so our function y equals x squared minus 9 over x minus 3, this is how it looks. It's basically the function y equals 3. Let me put the function y equals 3 over here, x plus 3. So the function y equals x plus 3 is just a line, 1, 2, 3, 1, 2, 3. It goes through these 2 points, and then it's a line, and it's a perfectly fine line. And now our function x squared minus 9 over x minus 3 is this same line but with a hole. Why? Because when x is 3, it's not defined. So it's exactly the same. 1, 2, 3. But then there is a hole. So we're gonna have a hole at 6, right? This one right here is 1, 2, 3. And this is the point 3, 6. So Our function is the same as the blue function x plus 3. It's just that our function has a hole at the point 3,6 and the blue function doesn't. But if you notice something, notice that actually we computed that limit and this limit turned out to be 6. But it turns out that 6 is the same thing as the limit as x approaches 3 of the function x plus 3. Okay? In other words, the limit of our red function as x approaches 3 is the same as the limit of the blue function as x approaches 3. And what's the difference between the red and the blue function? The only difference is that they do not agree at the point x equals 3, but away from 3, they are exactly the same functions, right? And actually, remember what we said last time, when you compute limits do not care about what happens at one point, at the point itself that you're approaching to. It's only about what happens around the point. So if around the point that you're getting close to, the two functions match, then the limits are going to match as well. That's the moral of the story that we want to exploit here. So note, for x different than 3, we have that x squared minus 9 over x minus 3 is actually the same as a function x plus 3. So in this case, the limit as x approaches 3 of the red function matches the limit of the blue function, and therefore is equal to 6. So in other words, every time that you have a rational function and you cancel something and you simplify a numerator with a denominator, what you're basically doing is you're changing your function with another function. This new function that you're getting is like this blue function, in which it agrees with your function almost everywhere except at one point, the one that makes the factor that you cancel 0. But as far as the limit is concerned, that doesn't matter. The value of the limits are not going to change. So you can replace the old function with the newly simplified one. Okay? So that means that if you wanted to compute this limit, now we don't have to be graphing anymore, nothing like that. You can just use the property. You can just say, okay, I can factor the top, like your classmate pointed out last time, and then say, okay, look, I can simplify these two guys. Now, by doing so, I'm going to obtain a new function, namely the function x plus 3, and I would like to take the limit of this function. Now, the function x plus 3 and our function, they are basically the same. It's just that they don't agree at 3 itself, but around 3, they are the same. So we can still write equal here because the limit is not going to change. Remember, limit does not care what happens at 3, but what happens around 3 in this particular limit that we're computing. And now, this is 6, and we are done. You compute this pretty easily in one line. No need to do table values, no need to graph, nothing like that. Okay? So I'm going to write what I just said here, the general property that basically says if two functions agree at all values, on an open interval around a given point, maybe they don't agree at the point itself, but if they agree around the point, then they have to have the same limit. Okay? So that property is going to take us to a lot of places, and that's basically the property that says that you can cancel stuff like this. You can cancel factors in a limit, and then whatever you obtain after you simplify, that limit is going to be the same as the original one. So you can keep writing equal sign. So that's a property that allows to do just that, simplify the limits. Okay, so theorem. Let a be a real number. Let a be a real number. And suppose that f of x equals g of x for all x different than a in an open interval. It doesn't have to be for every real number, but around a, okay? In an open interval containing a. So I'm not even telling you what happens at A. Maybe these functions are not even defined at A, or one is defined, the other one is not. Like in the case above, our rational function was not defined at 3, but the line x plus 3 is defined. It doesn't matter. Around 3, they were both the same, so the limits are the same. That's what I'm just going to say here. So suppose that f is equal to g for all x different than a in an open interval containing a, then if the limit as x approaches a of g of x exists, I should say this because this is my blue limit, like x plus 3. If this limit exists, then we have that the limit as x approaches a of f of x exists also, and moreover is equal to the blue limit. So if you, maybe f of x is something that you don't know immediately what it is, but if at some simplification you get your function g, then you can replace the limit of f by the limit of g, and the values will be the same. In other words, you can change the function f by another function as long as this new function only differs from f at the point a. But around a is the same, you're good to go. You get the same limit. So this is what allows you to do cancellations. Okay. Now let's do examples. Okay. Examples. Again, we already did one above. Okay. This one over here. Let's do more. So find the limits. And this is the property that most of the time help you whenever you get the 0 over 0 situation. Okay. So find the limits. Let's do limit as x approaches 1 of x cubed minus 1 over x minus 1. So here immediately, if the first thing that you should always try to do when you get a limit like this is plug in and see what you get. Okay, because maybe you just get a number and then you're good to go and you don't have to do anything else. In this case, if we plug in, then you see that in the top we're gonna get 0, and in the bottom we get 0. So we have 0 over 0. So this is what we call an indeterminate form. There will be 7 indeterminate forms that we're gonna discuss. This is the first one. Okay, this is an indeterminate form. We'll talk about indeterminate forms later after we talk about derivative. One of the first applications of derivative is that we're going to be able to look at limits one more time, and then look at some cases that we're not going to be able to deal with at this point because we need more knowledge. Okay. All right. So this is an indeterminate form. So what this means is that you cannot decide what the answer is by just seeing this 0 over 0. Okay. You have to do something about this. You cannot stay like that. So in this case, typically when they are rational functions, it's straightforward what to do. Remember that if you get a 0, it's because that polynomial that you have there was 0, either the top or the bottom. And that means that the number that you're approaching to is a 0 of the function. So x minus the number is a factor. You get this from precalculus, okay? So you can factor that polynomial, and then you cancel that factor. So in this case, that means because x cubed minus 1 is equal to 0, when you plug in 1, that means x minus 1 is a factor of x cubed minus 1. So we could factor that out and then simplify with x minus 1. Now, you either remember the property, remember that this is a difference of cubes, so you can factor it. So the way that we can do this is, okay, we have x cubed minus 1 over x minus 1. The numerator is a difference of cubes, so it factors as x minus 1 times x squared plus x plus 1 over x minus 1. Basically, the property that I use here is this one. So recall, if you have a cubed minus b cubed, this is equal to a minus b, and then a squared plus ab plus b squared. That's the difference of cubes. And since I'm here, let me also write the sum of cubes. So this is a plus b times a squared minus ab plus b squared. Okay, so and then using these properties, we factor, and notice that here we can now simplify this, and the new function that we obtain is a function x squared plus x plus 1. That function is the same as our function. It's just that they don't agree when x is equal to 1, but around 1 they produce exactly the same value. So that property from above is the one that allows to do that simplification and then exchange the first limit with this blue limit. Now we know exactly how to proceed. This is a polynomial, we just plug in. So we get 1 plus 1 plus 1, which is just 3. Okay, so this limit is equal to 3. Then let me say something about this in case you may be wondering, well, what if I don't remember this factoring formula? Or what if we get x to the 4 minus 1? What if it would have been x to the 4 minus 1 or x to the 5 minus 1? How do you do that? Because again, you can factor it, because as you know, if 1 is a 0, x minus 1 must be a factor. So I want to remind you that in those cases, what do? We do division, right? So since you already know that x minus 1 is a factor, or that 1 is a 0, we divide x cubed minus 1 by x minus 1, and then the quotient of the division will be the x squared plus x plus 1 that we obtain. Here you can either do long division or synthetic division. I'm going to do synthetic division because it's faster, just to remind you of this. Again, I'm reminding you of stuff that you learned back in pre-cal that you're going to need. That's why it's called pre-calculus, because you need those techniques now for calculus. Okay, so to factor x cubed minus 1, we may divide by x minus 1. I'm going to do it by using synthetic division. So remember how you do that. You put a 1 here, then you put the coefficients of your polynomial, x cubed minus 1, so it will be 1, then 0 for x squared, 0 for x, negative 1 for the constant term, and then, we create a little table like this. So the first number comes down, and then we do the following. We do this number times, so this number times whatever we have here, we put it here in the next column, and we add, and then repeat the process. Okay, so that's what I'm about to do now. Okay, so 1 times 1, that's equal to 1. You get a 1 here, and repeat. 1 times 1, that's 1. You add, you get a 1. 1 times 1, that's equal to 1. You add, you get a 0. Once you're done with the last column, we box the last number. That number is the remainder when we divide by x minus this guy, okay, which in this case was x minus 1, because the remainder is 0. That tells us that the division is exact, okay? So this is the remainder. And then this right here is the data that give us the quotient of the division. Now, you need to understand these numbers are the coefficients of the polynomial. So because there are 3 numbers, that means we have a degree 2 polynomial, and therefore the quotient is x squared plus x plus 1, because those are the coefficients, okay? And that's how you get this guy here. And then that means that our polynomial is x squared plus x plus 1 times x minus 1, which is the one that we divided by, okay? All right, so that was this example. Let me do a couple more, show you a couple more techniques, and then this will be enough for you to be able to compute some limits, and then do, for example, homework too. Then on Monday, I'm gonna do a couple more examples like this in person in case that you want to discuss something with me, and then we're gonna talk about other techniques, because this is not all there is to computing limits, okay? All right, let me do a couple more, and as I do so, I'm going to introduce you to other cases, other techniques that can be used. All right, so more space here. Let's do the limit as x approaches -3 of x squared plus x minus 6 over x plus 3. So again, if we compute this limit, then we notice that, for example, the bottom becomes 0, right? So the bottom is going to be a 0, and then the top is going to be, if you plug in -3, what do we get? We get 9, and then -3 minus 6, that's -9, so we get 0 as well. So it's a 0 over 0 situation. Again, we need to do something about it. Because it's a rational function, that means that we can just factor, right, and simplify. That will always be the case. So here we factor the top. Remember, you need two numbers whose product is -6 and the sum is 1. And we can do that. That's going to be x plus 3, x minus 2. So 3 and -2. 3 times -2 is -6, and 3 plus -2 is equal to 1. Again, if you don't find the numbers, remember, use division. You know -3 is a 0 at the top, so if you divide that polynomial by x plus 3, you will get the quotient, which is the other factor, which would be x plus 2. Okay? All right. Now we simplify, and we know that we can exchange this by the blue limit now, because our function differs from the blue function in just one point, -3. Around -3, they are the same functions. And now we just evaluate, so we get -5. It's an answer for this limit. Okay? All right. So let's do something slightly more interesting. That is not a rational function, but still the same idea. Limit as x approaches 0 of e to the 2x minus 1 or e to the x minus 1. Again, if we by inspection, you see that when you plug in, we get, so let me just to save space here. So we get 0 in the bottom, right? Because e to the 0 is equal to 1. So 1 minus 1 is 0. And in the top, again, we're going to get 0. So this is a 0 over 0 situation. So we need to do something about it. In this case, what we're going to do is, again, we're going to factor. But here it's a little bit more subtle, right? Because we don't have polynomials. But still, notice that e to the 2x, we can think of it as e to the x squared. So remember the property of exponents, that when you do the exponent of an exponent, you multiply. So e to the x, all of that squared is the same thing as e to the 2x, because you do 2 times x. So you multiply the exponents. Okay? Okay, so now that we are here, then we can see that the top is a difference of squares, right? So we can then factor that as e to the x plus 1 times e to the x minus 1 over e to the x minus 1. And now we can simplify these factors and once again exchange the previous function for this one, which they all agree at all points except as x equals 0, right? But around 0 they will give you the same value. And now we just plug in, which would be e to the 0 plus 1, which is 1 plus 1, which is just 2. So notice how we can now compute these limits without having to graph and without having to do any value, table of values, nothing like that. Just doing algebra, okay? Just doing algebra. All right, so we did these 3 examples. Notice that the basic techniques that we use in these 3 examples was factoring and simplifying, right? So we factor, so we got 0 over 0, and then we said, okay, we were able to factor, simplify, get rid of the problem that was giving us 0, and then we managed to compute the limit nicely. What if you have a situation in which, factoring will not do the job for you? In other words, that you cannot factor and solve the problem that way. What do we do? Let me give you an example. Let's say that we have something like this. Okay? The limit as x approaches 0 of this function over here. So again, the first thing that you should always do is plug in. Just plug in and see what happens. Okay? Okay, so we just plug in and then we see what happens. So if we plug in x equals 0, what happens in the top? In the top, we're going to have square root of 2 minus square root of 2. Again, that's just 0. In the bottom, we also have 0. So 0 over 0 situation. So what do we do in this case? What's the idea? Here, factoring is not going to do the job for us. So when you see this situation that you see radicals involved, one technique that you can try is multiply by the conjugate. Okay, so idea, multiply top and bottom by the conjugate. So that's similar as when you used to do to rationalize denominators. Remember when you have a radical in the bottom that looks like a binomial like this, what you do is you multiply top and bottom by the conjugate. Here is the same idea. So multiply top and bottom by the conjugate. Remember, conjugate is the same expression, but just to change the symbol. In this case, the conjugate of this is of the numerator is going to be the same, but instead of a minus, we put a plus. Okay. If it would have been a plus, then we'll put a minus. All right, let's do it. And let's see what we obtain. So we have square root of 2 plus x minus square root of 2 over x. So what I'm going to do is I'm going to multiply top and bottom by the conjugate. That's square root of 2 plus x plus square root of 2 over square root of 2 plus x plus square root of 2. Remember, this is happening inside the limit, okay? Now, remember when you multiply expressions like this, fractions, you do top with top and bottom with bottom. Now, why do we multiply by the conjugate? Because now the top is a product of two conjugates, so that's a difference of squares, right? And that's why this is helpful, because the conjugate now, when you multiply them, you get difference of squares, and those squares are going to eliminate the square roots that we have. So we're going to have, in the top, we're going to have the first guy square minus the second guy square. And then in the bottom, we get this product. We just leave it like this, okay? Let's not multiply, do not distribute the x. Let's see what we get. So that's the limit as x approaches 0. Now the square, square cancels square roots. So you get 2 plus x. And this one cancels this one. So you get minus 2. Okay? Over this expression. And now you should see what happens, right? Now the 2's cancel out here. So you only have an x on top. And then that x is going to cancel the x in the bottom. So that becomes limit as x approaches 0 of x over. That's why we didn't want to distribute the x in the bottom, because ultimately this x in the bottom, this one here, oops. So this x over here is responsible for this 0 down here. So we want to get rid of that x so that we don't have that 0 anymore. That's the reason why we're doing this. Okay. Multiply by the conjugate, and then after simplifying the top, an x come up on top that we can now simplify with this x in the bottom. Okay, so we can exchange this new function for this one, 1 over square root of 2 plus x plus square root of 2. But now this new function has no issues with x equals 0, right? We can just plug in, and then we get 1 over square root of 2 plus square root of 2, or 1 over 2 square root of 2. This is a perfectly fine answer, but if you want, you should rationalize. Remember, to rationalize, what you do is, so if you stop there, it's okay, but sometimes the problem will ask you to rationalize. So in this case, just multiply top and bottom by square root of 2. So you will get square root of 2 over, then 2 times 2, that's 4. Okay, these two things are the same. Okay, they're the same. It's just that the last one is rationalized, and sometimes you may want to rationalize, or you are asked to do it. Okay. All right. So, moral of the story. This was an example in which factoring didn't do the job for us, but the technique was multiplying by the conjugate. So if you see radicals like this, limits of this form, that you have a fraction, and then the top or the bottom has radicals, and you're getting 0 over 0, try this. Try multiplying by the conjugate of the term that has a radical, and then that may help you to solve the problem. Okay, let me do another example. That was number 4. Let me do number 5. So limit as x approaches 5 of square root of x plus 4 minus 3 over x minus 5. So once again, if we try to evaluate this limit, then we see that the bottom is 0. On the top, we get 5 plus 4, that's 9. Square root of 9 is 3. 3 minus 3, that's 0. So we have 0 over 0. So what do we do? Because we see a radical here, and there is nothing really that we can factor out, then the idea is, okay, let's multiply top and bottom by the conjugate of the term with the radical, which in this case is square root of x plus 4 plus 3. It's important, top and bottom, not just the top, okay? We need to multiply both sides, top and the bottom. Okay, so now on top we have a difference of squares, and as you know, that means the first guy square, which is just x plus 4, minus the second guy square, which is just a 9. And then in the bottom, we just have this product. Don't distribute, because our goal is, remember, to get rid of this guy, this x minus 5. We want to cancel it. That's responsible for this 0 down here. Okay? X plus 4 plus 3. Okay, so on top, we have now 4 minus 9, so that's a negative 5. So, you know, this is good, because now we have an x minus 5 that showed up on top that we can use to simplify the one that was giving us issues in the bottom. Now these two guys simplify. And remember, the main theorem for all of these examples is the one that we discussed above, that you can replace a function by another function as long as both functions agree around the point that you're taking the limit. Maybe not at the point itself, but around. And that's exactly what happens when you simplify. You get a new function that agrees with the old one around the point that makes the factor 0. Okay? All right. So now for this function, everything is fine. So we just plug in. So we get 1 over square root of 9 plus 3. So it'll be 3 plus 3. So we get 1 over 6 for this limit. Okay, so we have done several things here. I think this is a good place to stop. I don't want to really bombard you with a lot of information. I think you already have plenty of things here so that you can work on the homework, and now you can work on homework number 2. So on Monday, if you have questions on any of the examples that I have presented, you can ask me. If not, I'm probably gonna do a couple more, just so that you see them in person rather than just watching the video. And then we will talk about infinite limits. Those are limits in which the result is infinity. So we will talk what those means and vertical asymptotes. Then we're gonna deal with limits that give you infinity, limits at infinity. So what happens when x approaches infinity instead of just a number like we have been doing. And then we also need to discuss another special technique for computing some limits that what we have discussed so far is not going to be enough. Okay. After that, we talk about continuity, and then we will be ready for our test. So the first exam will be probably happening maybe not next week, but the following one. Okay. Remember, this theorem here is the main one that we are using for all of these algebraic manipulations. Okay, this is the one that allows you to simplify and still carry on with your limit. Okay, guys, so I will see you on Monday. I'm gonna stop recording now.